All right, how's this? I do see it now flickering on my thing, so hopefully that should be good. Do, 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 do. Yes? Awesome. Cool. Sorry about that. Thanks for pointing that out. So, okay, then let's start over. So, last time we talked about chemical reactions. We kind of started our introduction. We looked at types of reactions, um, and we kind of were looking at predicting the products of those, and kind of just seeing how those reactions worked. There is one thing that I guess I kind of forgot to mention about single replacement reactions, and that's when you have something that has a variable charge with it. So something like iron, for example, we know that in a single replacement reaction, charges do change, right? We're going to end up kicking out our aluminum, replacing it with iron. And so we have kind of options here. We could make the iron 2-1. We could make the iron 3-1. But we don't quite know, right? That's something that we end up talking about in Gen Chem 2. So that would be 113 would be the class number. So this is something that is beyond the scope of this class. So what we do is we just kind of use a rule of thumb and say if you have to choose a charge for a variable charge metal or transition metal, we are going to just have a rule for us that says, okay, in this class we always choose the +2 charge if we're given a variable charge metal that needs to make a compound. So if you were to think about that in, say we had, I don't know, how about manganese plus oxygen in a combination reaction? We're going to want to make the +2 one for that. So it's going to be the case for if we have these kind of variable charge metals that we're not quite sure which charge to use. So in this class, we're just going to choose +2 across the board for predicting products of chemical reactions. All right, so for us, transition metals, except silver, of course, get a +2 charge in ionic compounds in, or let's say formed in chemical reactions. Remember, silver is always +1, so we don't have to worry about that. Zinc and cadmium are the other two transition metals that have fixed charges, but they're +2 anyway, so we're okay. And Oz has already started the borking. That's great. Fun. Okay, so that was yesterday's stuff. Just kind of clarifying that point there. So, let's go on to new stuff. If we want to kind of complete our chemical reactions, we have a lot more information that we can include. For example, we often like to include states of matter in reactions. This is going to be important for us so that we know what state of matter our reactants are in. So if we want to duplicate the reaction, if we need something to be solid or if we need it to be gas, or if we're trying to predict, is a solid going to form from this reaction, it's helpful to know the states of matter because that's going to help us be able to kind of work with these things. So we, of course, have our 3 normal states. And then we're going to throw back in that aqueous one, because we're going to see a lot of the chemistry that we do in this class is going to be water-based, things that happen in solution. So we're going to see aqueous quite a bit here. Okay, so we have, of course, solid, liquid, gas, and aqueous. Remember, aqueous means dissolved in water. And so aqueous reactants are very common for us. So we're going to see that solids will not really be able to react by themselves very easily. So since a lot of the compounds we deal with are normally solids at room temperature, we dissolve them in water to be able to have them react with each other. Because things in solids, remember, can't move around. If they can't move around, they can't react. So typically we're going to see aqueous as a very common state of matter for us. So, how do we know what the state of matter is going to be? Well, we kind of have several kind of ideas here. The easiest ones for us would be just elements in their natural state. So if we want to think about elements by themselves, so like the iron or the manganese or the oxygen in these last two equations here, if we were to predict their state of matter, we can just kind of look at the periodic table. If we find our periodic table and open it, I hope this one has a nice way of showing it. No, I'm not going to pay for you. Okay, this particular one doesn't really show it, but many periodic tables will color code various elements on here. We're going to see that most are solid. We have a few that are liquid. Which are mercury and bromine. And then we have the gases, which are going to be chlorine, fluorine, all of our most of our diatomic elements are here, and then the noble gases are going to be gases. Everything else is going to be a solid. So if it's by itself. So if we were to take a look at that reaction we did before, I'm just going to tell us that one's going to be solid. If we were to look at these two are elements by themselves. We would have to find manganese on the periodic table. Again, many periodic tables do show the state of matter with various color coding. Suffice it to say, all of our metals, except for mercury, are solid at room temperature. Manganese is kind of right here, right in the middle. That's going to be a solid at room temperature. And oxygen, hopefully we know, typically should be a gas at room temperature. So typically we're looking at room temperature for these reactions. And so we can just go with what the standard states of matter are on the periodic table. All right, so hopefully nothing too crazy there. But it's when we get to compounds that things get a little bit tricky. So perhaps we should start with the aqueous state of matter. A compound in the products is aqueous with two conditions. At least one reactant is aqueous. So in order for it to be aqueous, there has to be water around, right? So if your reactants do not have water anywhere with them, there's no reason for a product to be aqueous either, because there's no water to dissolve it. And so we need at least one reactant to be aqueous. And we're going to see that by and large, most reactants that we deal with will be aqueous. And the other kind of criterion that needs to be met is that it needs to be a soluble ionic compound. So we may want to remember the solubility rules. So hopefully that, well, I guess we can quickly go over those again. So soluble things. The first one was stuff with sodium, potassium, lithium, ammonium, nitrate, and acetate. ClBr or iodine, except lead and mercury. And then the last one we had was things with sulfate, except calcium, barium, strontium, and then those same ones from before. So those were our solubility rules. Everything else we want to say is going to be not aqueous, essentially. Okay, so anything that has these guys, we're going to expect to be soluble. So for example, just so you know, typically you're going to be predicting the state of matter of products. Because you could be given your reactants in whatever state that I feel like giving them to you in. But predicting the products is where we're going to want to focus our energies in predicting the state of matter. So, as we can see here, I've just given you reactants. So if we wanted to actually figure out the states of matter for our products, we first need to figure out what those products are, right? Hopefully here we can see that this is going to be a double displacement reaction, right? We have two ionic compounds. We have the lead-2 ion and the iodide ion. So we are going to get PbI2. And the other combination we have will just be KNO3. If we want to look at the state of matter of these, we have to check if they're going to be solids or not, if they're soluble. So do we have at least one aqueous reactant? Yeah, both of our reactants are aqueous in this case, so we're okay. Do we have soluble ionic compounds? Let's check our solubility rules. Hopefully the second one here we can see right away. That one will definitely be aqueous because we have both potassium and nitrate in it, so it's always going to be soluble. However, if we look at that PbI2, we see we have an exception to our rule about iodides. So this one will not dissolve. It is not soluble. And as a result, we indicate it as solid. So because the lead 2 iodide is insoluble, it forms a solid in solution. We also call this a precipitate. And I have a video of this. We've actually seen this video, I think, maybe in this class. Let's take a look at this particular reaction. Yes. So we have our two aqueous components here. You can see they're, again, happy two aqueous reactants. They're both dissolved in water. In they go. We're going to add them together. And we form this yellow gunk, which, if we kind of look at the end of the video here, you can kind of start seeing it settle at the bottom. It is a suspension, so it does settle out later. We're going to see that this is proof that we have a solid being formed in this reaction. So our prediction that this reaction produces a product that is solid is supported by the reaction evidence we have here. Color changes are kind of a separate thing. We're not going to really worry about color changes too much, but this one had produced a solid. So we're going to see that solids will form anytime we have ionic compounds that are insoluble. So we're going to see many of these. So another example would be something like, I don't know, how about we put calcium chloride plus, how about zinc sulfate? Put those as aqueous. Again, you don't have to worry about predicting it for the reactants. You want to predict it for the products. Hopefully we can see here double displacement reaction is going to be taking place here. We're going to end up swapping the two. And so we want to go ahead and check our solubility rules. So we do see that we do have aqueous reactants, at least one, so we're good there. Let's check our solubility rules. Okay, so our first compound was zinc chloride. Chlorides should be soluble. Zinc is not an exception, so we are expecting that zinc chloride should still be aqueous. Calcium sulfate, let's look up our sulfates. It looks like calcium sulfate is an exception to the rule, so calcium sulfate should not be soluble. If it is not soluble, it's going to be a solid in our reaction vessel. So it does not dissolve, it's going to stay solid. All right, so hopefully this is kind of a review, since we just did this kind of last chapter where we talked about solutions. So it may be a good idea for you to go and check your rules about that again. Let's do just one more though. Single replacement reaction here. Copper is a variable charge metal. But remember, with variable charge metals, we want to kind of use the +2 form. So if we do that, remember we're going to be kicking out our silver. Silver, of course, would be solid because it's an element that is a metal. Metals are typically solid. Except for mercury. Our other compound would be the copper 2 nitrate. We would expect that one to be aqueous, hopefully, because we see the nitrate there. Anything with nitrate will always be soluble. If it's soluble, we're going to see it's going to be aqueous in the reaction. What's interesting to note, just so we, for our own information, silver ions are clear in solution, but copper 2 ions are bright blue. And so we can actually see evidence of this happening. I have another video for you where we can see this very reaction taking place. So we have our clear solution of silver nitrate. We have our copper metal. This is a time lapse here as we go. We see silver forming, right? We see not quite crystals, but kind of crystals of silver metal forming on this. And looks like snow, doesn't it? Back in winter semester. And so we can see all that kind of silver gunk coming out here. So we can see all that lovely silver. And then you can hear me talk about it. I think if you watch the videos, I make a mess dripping it everywhere. But you can see also very clearly that the solution now is blue. It was clear to start, now it's blue. That's indicative of dissolved copper ions. That's not something you'll need to memorize, but that's, again, proof that this is happening. So we're forming solid silver. That's at the bottom of our reaction here. And we're forming aqueous copper ions in the form of copper 2 nitrate. So, again, we have evidence of these solubility rules here. Okay? So, that's solids then. So solids will be either elements that are solid at room temperature, like silver, or they would be compounds that are insoluble, like calcium sulfate, or what did we do before that? Lead 2 iodide? Yeah, lead 2 iodide would be another one. Silver chloride is a common solid that you find in chemical reactions too. So, that's solids. Any questions on predicting solids in reactions? All right. What about liquids? Thankfully for us, there's really only 2 liquids that we're going to really deal with. One, of course, being water. The other one being bromine. We might also see mercury, but that's much less common. So these are the only things that will be liquids in our reactions. So lucky us, we don't have to worry about that. One thing to note in combustion, though, we have water as a gas. Just because it's so hot, obviously combustion, fire taking place, we're going to have gaseous water. Excuse me. But in the chemical reactions that we're going to otherwise deal with, like double displacements, for example, we're going to see that water will be liquid. Let me make that a little bit obvious for us. So, for example, if we take common acid-base reaction here, double displacement, of course, we get HOH plus NaCl. Remember that HOH, it's just our dear friend water. Of course, the water we would expect to be liquid, and the salt will be aqueous, of course. We know that sodium salts are soluble in water. All right, I guess I can give you these as well. These will, of course, be given to you. So, nothing too crazy here. Really, most things that form water will be acid-base reactions. We can look at one of those. I have a video for you there as well. Let's see this one. What's interesting is that when you form water, when reacting things, you often release quite a bit of heat. So you can see all the steam coming off this, and you can see the thermometer here just zipping up. You can kind of see some dissolved gases bubbling out as well. So when you're producing water in reactions, you often do get a lot of heat. But we'll talk about that later. So really, the only time you're going to see a liquid is if you have water or bromine, rarely mercury, but we don't typically use elemental mercury in reactions, so it's not as common. Elemental bromine we use. Those are kind of the only situations you're going to have. Well, here, let's just do another one. How about we do KBr plus Cl2? If we do this, we're going to get bromine liquid plus KCl. This is a single replacement reaction. We did this type of thing, I think, similar reaction yesterday. Maybe we use sodium instead, but same idea. Kick out the non-metal. Remember that bromine and chlorine are both diatomic. We're going to see that the bromine would be liquid here. All right. So those are really the only two liquids you see. So hopefully just learn those two. The rest you don't have to worry about being liquids. The liquids are easy. And what about the last one? We've got gases here. So we're going to see that we have, as elements, we have chlorine, fluorine, oxygen, nitrogen, hydrogen, and then the noble gases. Although we will not see the noble gases in reactions typically. Those would be elements that form gases if they were to be produced in a reaction. But for compounds, we have a few kind of special scenarios. We're going to see that if we have what are just kind of unstable products that form gases. And we're going to have a few of these. One of them is carbonic acid. We're going to see that this one will very quickly break down into water and carbon dioxide. This is the reaction that happens when you open a soda can, for example. Or perhaps you may have remembered your elementary school chemistry. We'll take a look at a video of that later, but I want to show you the kind of four reactions that will produce gases here. Another one will be sulfurous acid. That one will also be unstable, and it will break down to form liquid water and sulfur dioxide. So analogous to the last one, just sulfur instead of carbon. Ammonium hydroxide. Is another one. And then the last one is just hydrogen sulfide. Anything that produces hydrogen sulfide is a gas already. So we're going to see that if these are products we must break them down. All right, that would be these three. If you have something that produces one of these three compounds in a reaction, we have to break it down. Let's take a look at an example of it. Our favorite, one of our favorite reactions. Two ionic compounds. This is a double displacement reaction. All right, so if we just swap things around, we get our products, both of which are aqueous. We have an acid, acids are aqueous, and we have a soluble ionic compound. But we know that if we were to mix these two, vinegar and baking soda, together, we do get a gas. We have seen this many times, right? But if we ever see one of those three compounds in a reaction, we have to break it down. So really, this reaction is better described as producing sodium acetate plus water plus CO2. This would be a better way of describing this. So the carbonic acid that's produced will immediately break down into carbon dioxide and water as it's formed immediately. And I mean, I'm sure you've seen vinegar and baking soda, but why not? We have a video. Let's go ahead and take a look. If we were to just mix these, again, we're going to expect, we're just going to have two aqueous products, but as soon as we do this, of course, we see definitely a lot of gas is being produced here. So here, we can watch it again. In it goes, bubbles like crazy, all because of that decomposition of the carbonic acid. It breaks down immediately into H2O and CO2. So anytime you see one of these three underlined products in a reaction, you've got to break them down into water and whatever the gas is. Those are going to be the ways that we see gas coming out in reactions. The last one is if you just produce hydrogen sulfide, it's a gas. There's no breakdown associated with that. That would be something like if we were to take, let's go back to black. This plain double displacement reaction, if we were to take these two, we would see the hydrogen sulfide would be a gas. That's your rotten egg smell. You'll know right away that you've produced hydrogen sulfide because it will start stinking up the room as you do that. So that's kind of the other one. Let's do... I think let's go ahead and do a couple of mixed up ones. So we've looked at all of our states of matter. They're kind of somewhat in our heads. Let's go ahead and practice with them just to make sure that we've got all of this kind of, at least apply it, Let's do a few practice problems. Remember, there is that worksheet on Canvas that will ask you to predict the products as well as the state of matter and all that. So, there is more practice there as well, and it does have the answers. So, it's always a good idea to practice more. So, So with this, let me give you a couple of reactions, and let's see what we can do with this. And let's do another one. All right. So let's go ahead and practice predicting the products and the states of matter of these three reactions. Again, if you're watching this at home, it'd be a good time to pause it so you can take some time to practice them, especially if you want more practice just kind of predicting the products without the state of matter, just kind of doing the double displacements on your own. All of these are double displacement, by the way. I guess I had just chosen that one. It's probably the most common type we're going to see in this class, so we'll see a lot of double displacement. So if you are wanting time to predict the products yourself, pause the video, do it, and then restart. I'm just going to go ahead and put the products right away. And then we have... So make sure you do get these as your products. Just double displacement, so we're swapping them all, charge balancing appropriately. If we want to look at the state of matter, we want to look, okay, zinc carbonate. This is an ionic compound. It's not one of our gases. It's not one of our liquids. It potentially could be a solid. So we have to check our solubility rules. We see we do not have a rule for carbonates. And remember, if we don't have a rule for it, we are going to assume it is insoluble. If it is insoluble, we're expecting it to be a solid. Therefore, we'll see most carbonates will be solids. All right, and of course, sodium chloride should be aqueous. We have sodium in there, we have chloride in there. Both of them are going to be aqueous. Same thing with the sodium nitrate. Hopefully we can see right away that one should definitely be soluble. This ammonium hydroxide business, well, you might think, okay, that should be soluble, but ammonium hydroxide is one of our special cases where we are not going to write it as ammonium hydroxide. We're going to write it as water plus ammonia. That's one of these three gas-forming products. So we have ammonium hydroxide there. That's one that breaks down. So again, you'll just need to, unfortunately, commit these three to memory. And if that's the case, the water will be liquid and the ammonia will be gas. So we don't actually write NH4OH, we will write the water and the ammonia. All right, last one. Hopefully we remember water should be liquid. And then our other compound, we have a compound with lithium, so it should be soluble. Sulfates are also generally soluble, so we're going to see that that one will be aqueous. So typically we have one aqueous product and one other one, so we have a solid, liquid, and gas here. So you'll want to practice these. On those practice ones, you'll probably want to just practice doing the states of matter anyway. That one worksheet does have states of matter included with it. The online thing, I don't remember if it has states of matter, but it would be a good idea to practice. And you can just throw it in Discord, hey, I was doing this one online, and I was just wondering, is this going to be something that produces a solid or not, or, whatever. Just throw it in Discord. your classmates can help you out. I can help you out, just to make sure that you're on the right track. Because all the stuff just takes a ton of practice to really get down. Because there's a lot of rules, right? So you'll want to do lots of practice with these. I think your double displacement worksheet also has states of matter included on there, so you'll have some more practice with that as well. So let's see. We're going to see that in a reaction, here's our cheat sheet. All right, if we have insoluble ionic compounds, or when we're going to form solids. So we need to use the solubility rules. If we're going to form a liquid, that's just going to be water or bromine. If it's a gas, we have the option of hydrogen sulfide. And then we have the breakdown of the breakdown products of these three will also produce gases. All right, and then of course we have any of our elements that are gases as well. So this is going to be kind of our cheat sheet. I guess I could write this. So solid elements as well. Kind of have two ways to do that. And then we have the gaseous elements. Could also be gases. And why not? Let's just throw mercury on there as well, because why not? Even though, again, it's not a very common thing that we're going to see. So, lots of stuff today. But we have more to do. Let's just take 30 seconds to kind of reset our minds here. So, get up for a sec, stretch. Just cleanse your mind for just a second here before we move on to the next little bit. Or we're going to finally deal with those pesky subscripts that we keep seeing. So, let's go say hi to Oz, perhaps. Come here, buddy. Come say hi to everyone. Hello, he says with his tongue. Are we ready to talk about balancing reactions? I think we are. Alrighty. Here we go then. So this is where we're going to see that kind of law of conservation of mass and matter coming into play here. Because we're going to see that the number of atoms of each type must be the same on both sides of a reaction. He's licking my hand. I'm sure you can all just hear that lovely sound. Oh, Oz. Let's take a look at an example here. Oz, you're gross. Okay. So, if we look at this, if we want to think about what this is looking like, colorfully speaking, have the hydrogens like that. We'll have the oxygens be light blue, perhaps. Make them a little bit bigger. So this is this kind of reaction, right? And I've just drawn them as little molecules to help us see. If we want to look at the reactant side, and the product side, we have two elements in this reaction, right? We have hydrogen and oxygen. If we just kind of take a look at where we are right now, on the reactant side, we have 2 atoms of hydrogen. On the product side, we have 2 atoms of hydrogen. We can see that. Those are the black dots. So we can see here across our reaction, we have 2 black dots on both sides. So hydrogen's okay. Creature's dying down there, it sounds like. We have 2 oxygens on the left, but we only have 1 on the right. So this reaction is not balanced. We're going to see that we're going to need to fix this. Creature, you don't have to like die down there. Come on. His trachea collapses sometimes, and so that's the sound he makes while popping it back open. It's not harmful or anything, but it's very loud. So with this, one thing to note, we can never change the compound formula. We can't just say, okay, you know what, I'm just going to throw a 2 on there, and now we're balanced. No. Because now you're changing the compound that you're forming. You know, we spent all this time predicting what products are going to form. It'd be quite silly for us to... Shh, creature, relax, buddy. Oh my gosh. Is it that loud? I wonder, can you guys still hear me like over him doing that? Well, we'll see. So what we have to do is we have to change the number of the compounds that we have here. So if we need more oxygens on the right side, well, why don't we just throw in a second water molecule? That way we'll have enough oxygens. So now we have 2 water molecules. And now, we'll have our 2 oxygens on the right side that we were looking for. But also that means we've changed the number of hydrogens. So now we have 4 hydrogens on the right, but we only have 2 on the left. So the solution here, well, we can just throw in another molecule of hydrogen. And that will now make our reaction such that it is balanced. And so we can see it not only kind of in the pictorial form here with the dots. We see we have 4 black dots on the left, 4 black dots on the right, 2 blue dots on the left, 2 blue dots on the right. But we could also see, if we were to just count the elements in our formulas for our chemical compounds here, that we should have a balanced reaction overall. How does that look? This is the process that we're going to be doing through this. I'm not going to be drawing pictures every time, but that's what's happening here. So remember, we can't change our formulas of our compounds, but what we can do is throw more of them in there. So we just threw in an extra hydrogen molecule, an extra water molecule, and now everything is balanced overall. And so we are happy. That is a balanced reaction. If we take a look at another one, here's one, and I'll even give us the states of matter just for our practice. If we take a look at this reaction, if we want to see on the reactant side and product side if things are in balance, I like to make a little table of all of the elements here. And let's just count right now where we are, and then we'll adjust as necessary. So on the reactant side, we have 1 zinc. On the product side, we also have 1 zinc. we have 1 iron on each side. And on the reactant side, we have 3 chlorines. On the product side, we have 2 chlorines. So, things are not in balance here. We can't just say, okay, let me add another. If I add another zinc chloride, if I do this, I'll have 4. Right? But that's kind of a silly idea. It's probably a little bit easier for us to just do the least common multiple like before. If we know that these two numbers are not they won't work with each other, the 3 and the 2, let's make them both into 6s. And that way they can be the same. If we are going to do that, that means we have 3 of these and 2 of those to balance out the chlorines. Right, so the least common multiple between them. Since we can't just say, okay, we can't just throw in 1 more zinc chloride. It's gonna now we have too much zinc chloride. Now I have to go back to the other side, and eventually you'll end up with this. But just faster to just go directly to the least common multiple. Note, however, that does change a few things. That does change our zinc on the left and our iron on the right. So if we want these to be balanced, well, we can just make this one have 3. That'll take care of the zinc. And if we make that one have 2, that'll take care of those. We can now check all of our atoms are in balance to each other. We have 3 zincs on each side, 2 irons on each side, and 6 chlorines on each side of this reaction. So now it is balanced. How about another one? So you see how easy it is, by the way, for me to just throw things at you? Since all I have to do is give you 2 reactants, I can have you predict the products, predict the type of reaction, predict the state of matter, and then balance it. So I can have you do 4 things now just by giving you 2 compounds. So there's lots of stuff I can do with this. And so that's why I kept saying it's going to keep building on itself. So make sure you practice these so you don't get behind on it. If we do predict the products, we do get these. I have, and if we look at the states of matter, we should get those. One thing to note for balancing, you want to keep your polyatomic ions together. And what I mean by that, if we take our reactants and products, instead of doing oxygen and phosphorus separately, let's just keep it as phosphate. So let's not even worry about splitting those up, because that's just going to make it more complicated for us. We're going to see polyatomic ions typically do not change over the course of a reaction, so we don't need to worry about them splitting up or anything. So we can just count it as a phosphate. So let's go ahead and take a look at the number of each we have. We have 3 sodiums on the left. That's what Na3 means. Na3PO4 has 3 sodiums. We have 1 on the right. Phosphates, we have 1 on the left, 2 on the right. Calciums, we have 1 on the left, 3 on the right. And then chlorines, we have 2 on the left, 1 on the right. So let's just kind of go just down the line. Let's see what we get. If we want to make our sodium have 3 on the right, we can do that. by putting a 3 in front of sodium chloride, which will also bump our chlorines to 3. I'm just going to keep going down the line. Next is phosphate. We have 1 on the left, 2 on the right, so we're going to need another phosphate here. That's going to bump our phosphates to 2, but it's going to bump our sodiums to 6. We can either address the sodium now or keep going down. Doesn't really matter. If we want to adjust it now, we see we have twice as many sodiums on the left as on the right. So if we want this to be 6, we can just adjust our coefficient here. Get rid of that. Now it's a 6. That brings our chlorines to 6 as well. And then if we look at our calciums, it looks like we have 1 on the left, 3 on the right. So let's go ahead and put a 3 here. That'll bring our calciums up to 3. And that'll also bring our chlorines up to 6, which is what we wanted anyway. And so now we can see everything is happily balanced out. So these are the what are called reaction coefficients that we get from balancing this reaction. So we're out of time today. Tomorrow we'll continue, or not tomorrow, Monday, we will continue balancing reactions. We'll take a look at more complex examples. Your homework is not going to be due this weekend, just because we haven't covered everything yet on it. So I would definitely suggest working on it. Take a look at those practice websites that we have. So get on that. That's what I would suggest doing. Practice these. You know, even if you do the worksheet, 2 days later, come back, do that like 6 problem worksheet again. Make sure you can, balance and do all these things with your eyes closed, by the end of it. So practice. That's going to save your life in the next exam. So, yeah, cool. All right. See you guys next week. Enjoy your weekends. As always, if questions come up over the weekend, drop them in our Discord chat, and we can talk about them. So awesome. All right, see you guys later.